Okay. I believe where I left off was at the end of problem 3, correct? Mixed up the light so I can use this part of the chalkboard now. Don't know why I didn't think of that before. So it kind of rushed at the end, and I want to make a couple of comments. The reason that the voltage, well, the difference in voltage, delta V, the potential difference, the reason it's negative is because if you move from point A to point B, the potential decreases. If you went the other way, it would be positive. Electric field lines point toward a lower potential. Just like a gravitational field points toward a lower elevation, an electric field points toward a lower potential, which in this case would be toward the right. So as you go from A to B, you're moving, well, aside from any movement across the field lines, which doesn't matter, you're moving along the field lines, you're headed toward a lower potential if you go from A to B. So field lines point down in the sense, not necessarily horizontally down, but they point down in the sense of toward a lower voltage. Next example. An electric dipole, once again. I established at the end of section 1 that at large distances, meaning large compared to the distance between the two charges, the field of a dipole is an inverse cube. The example we did the other day was actually somewhere down a line that's perpendicular to the axis of the dipole. Here we're on, we're along the axis that runs through the two charges, but it's still true that the combined effect is an inverse cube at large distances. So given that E is 200 over r to the third power, we're supposed to find the potential difference between x equals 2 and x equals 3. The thing that's different is in the previous question, you had a uniform field, so it was just volts per meter times meters gives you volts. Here, it's a field that changes as you move from one point to the next. So you have to integrate. You have to take, if you imagine a test charge moving from, which way is it going? V2, it's like anything else, delta V is final minus initial. So it would be moving from x equals 3 to x equals 2. It's getting dragged toward the dipole, some little test charge on the x-axis. And so you have to take that entire displacement from 3 to 2 and chop it up into many, many little increments. You take the limit of infinitely many, infinitely small displacements. In other words, potential at B minus the potential at A. This part I'm just copying directly off the formula sheet. suppose they could have gotten rid of the minus sign just by switching the limits of integration, but this is the way it's written in the textbook, so we'll just play along with that. Anyhow, what we're dealing with in this particular problem is the potential at x equals 2 minus potential at x equals 3. Fill those in for the limits of integration. The formula for E is given in the question, so I filled that in where the E used to be. And since, well, actually, I suppose I could have called it dx since we're moving along the x-axis, but since I'm calling the distance r, I'd like to make it match. So you're moving directly away from the dipole along some radius vector r, and each little infinitesimal change is dr. So ds is the same thing as dr in this case. A constant can be taken out in front of the integral, get it out of the way so it's not cluttering up what you're trying to do. Maybe I should write it this way. Integral of r to the minus 3 would be r to the minus 2 over negative 2. With a definite integral, you don't bother writing down the constant of integration because it just drops out anyhow. When you know, to evaluate this, you evaluate it at the upper limit and you evaluate it again at the lower limit. And when you subtract those, the constant of integration would cancel out anyhow, so people don't bother writing it down. This minus sign cancels that minus sign. And for that matter, 200 divided by 2 is 100. So you've got, fill in the 2, and that's 1/4. 2 to the minus 2 power, 1/4. And then 3 to the minus 2 power is better known as 1/9. Potential difference between those 2 points is 13.9 volts. Maybe I'll return one more time to the issue of minus signs, because I was sitting in my office this morning looking through my notes before class like I always do, and I'm thinking like, wait a minute. Now, if you go from 3 to 2, the displacement is to the left, but the electric field points toward the right. So wouldn't the dot product give you a cosine of 180 degrees? And that's a minus sign I didn't include here. And I thought about it for a while and eventually figured out what I was overlooking. But the point is, minus signs are evil. They are all, there's always another minus sign you didn't think of waiting to get you. So it's good to have some physical sense for what's going on instead of just blindly throwing numbers at formulas. The electric field, like I said back here, points toward a lower potential. So in this problem here, the electric field points to the right. If you are moving from 3 to 2, That's moving against the field lines. That's moving our positive test charge, a proton or whatever it is. It's moving it toward a higher potential. So the potential should be increasing. Delta V should be positive if you're moving against the field lines. Delta V should be negative if you're moving with the field lines. So in the end, maybe it's best just to think of it that way. There's a part B to this. Probably I should have labeled this as being part A. This is part B. How much potential energy? So now part A is asking for potential, which is volts. Part B is asking for potential energy. Energy is joules. And they're related to each other. Like that. That's the definition of potential difference. That's something you're supposed to know. You won't find that on your formula sheet. You'll just find a little note that says you're supposed to know it. A volt is a joule per coulomb. Energy per unit charge is potential. Well, delta U is the thing that's being asked for here. Multiply both sides by Q and then fill in the numbers. Charge on a proton is the same as the charge on an electron, except that it's positive. Potential difference is the answer from part A. You multiply those together. 2.22 10 to the negative 18. Okay, so maybe I should top the page for a moment. Up at the top of the page, just above example number 2, I had a uniform electric field. Okay, that's one special case that we'll look at fairly often in here because it's simple. You have a uniform field, you don't have to integrate, you just use some 9th grade mathematics. But another special case that comes up fairly often in here is the field around a point charge or a sphere, the type of situation that Coulomb's law describes. So between parallel plates, when you've got a uniform field, it's V equals E times D. Maybe I should have mentioned before, where V equals 0 is an arbitrary choice you get to make. That's just like when I was talking last fall about the gravitational case. Gravitational potential energy of this stapler, mgh. Where do I measure h, the height, from? Should I talk about how high it is above the floor? Should I talk about how high it is above the table? Answer is it doesn't matter. Once you make a choice, you have to stick with it through the whole problem. But the original choice is completely up to you. You can measure it from the ceiling if you like negative numbers. It's the same with electric potential energy and therefore with electric potential. You can put 0 any place you find convenient. With parallel plates, the convenient choice would seem to be to have it at the negative plate. So like I labeled down there, we will choose to say that the potential is 0 at the negative plate. And however many volts E times D is equal to. That's the potential at the positive plate. The potential would steadily drop in between. For a point like charge or charged sphere, well, the force is given by Coulomb's law, and you know, while I'm at it, I might as well cover the gravitational case. Same thing I said a few days ago when I was talking about some other stuff. Electric fields and gravitational fields are kind of the rerun of the same story, so let's just do both at once. That just seems kind of efficient to me. Either way, you are talking about an inverse square force field. Something of the general form F equals K over R squared. K is, in the case of Coulomb's law, it's the Coulomb's law constant times Q1 times Q2. In the case of a gravitational force, K would be the gravitation constant times M1 times M2. Either way, you've got some other numbers over R squared. Both forces behave the same way. So what's the potential energy of an object in an inverse squared force field, whether it's electric or gravitational? Well, energy just means stored up work. Work is the integral of F dot ds, force times distance for each little increment of the distance that you move the charge or the mass. For the force, I'll fill in K over R squared, like I was just talking about. See, it's like if it's Coulomb's law, for example, you have here some charge that's creating the electric field. You have some little test charge here that feels its effects, and you're going to move it from there to there. That's ds, okay? And while it's moving from there to there, this K over R squared force is pushing on it. Well, if altogether the thing is going to go from there to there, you have to take that entire displacement, cut it into lots of little pieces, add up the work done in each little piece. Each little piece is F dot ds. Let's say that the test charge begins at a distance that I'm going to call little r. I used big R and little r to distinguish my variable of integration. Little r is a constant. That's how far away this thing starts out from the charge producing the field. Capital R is a variable. It gets bigger and bigger as the thing moves away. Okay, so capital R is my variable, little r is the lower limit of integration. With a case like this, the convenient place to put an energy of zero and a potential of zero is at infinity, which, you know, infinity seems like maybe not necessarily the easiest thing to use, but it is. I guess one way of explaining it is to say that the force that this exerts on that gets smaller and smaller as it gets further away. You'd have to have it infinitely far away for there to be no force at all. And that's where we think of the test charge as having no energy, okay? If it's not interacting with this other charge at all, it has no potential energy, and that would happen if they were infinitely far apart. So the formula would take on a more complicated form if you said that the potential energy was zero somewhere else. So how much work is needed to get from R initial to infinity? You integrate some constant times dr over R squared, And once again, I'm going to kind of do a quick and dirty version and not explain all the minus signs that are just more trouble to explain than they're really worth. The main point that I wanted to point out is that if you integrate 1 over r squared, you get 1 over r to the first power, okay? So if the force goes as 1 over r squared, the potential energy that something has due to that force goes as 1 over r to the first power. And that's written on the top of the next page. Gravitational potential energy looks just like Newton's inverse square law for force, except it's r to the first instead of r squared. Electric potential energy looks just like Coulomb's law, except it's r to the first instead of r squared. As for plus and minus, Newton's, the force, the equation for force doesn't have a minus sign in it. Newton's inverse square law for force. The way this works is that if you have an attractive force, the potential energy will be negative, because if this is attracting that, you've got to pull it away to get it out to infinity. Of course, if you're talking about an atom, infinity is basically half an inch away for all practical purposes, but however far away it is to be effectively at infinity, you have to add energy. You have to do work on it against attractive forces to pull it out there. So if you have to add energy just to get it to an energy of 0, that means it started out with something negative. That's why there's a minus sign on there. As for the electric version, the minus sign takes care of itself automatically, because if it's an attractive force, one of the Q's is positive, one of the Q's is negative. If they're both positive or both negative, then the potential energy would be positive. If you have a repulsive force, this pushes that away, and this charge here could do work for you on its way to infinity. And so if energy comes out on its way to having 0, then it started out with a positive amount of energy. The potential, V, volts instead of joules. Well, potential is energy per unit charge. The per unit charge cancels out one of the V's, or I'm sorry, one of the Q's gets canceled out from the equation just above it. So the voltage at some point around a point charge is the Coulomb's law constant times Q over R. An example, and I decided to go with a gravitational example. Let's, just for the heck of it, calculate the Earth's escape velocity. Or, just changing to different numbers, this is how you would get the escape velocity from any planet. It's a conservation of energy problem. Okay, escape velocity means if you launch some projectile, maybe straight up, okay, you've got some enormous cannon. The barrel on this cannon is like half a mile long or something like that. And you shoot some projectile upward with some tremendous velocity. How fast would it have to be going to never come back down? The old saying, what goes up must come down. Well, you don't want to take old sayings entirely seriously all the time. If you just give something a little toss, it comes back down right away. If you throw it harder, it takes more time before it drops back into your hand. If you throw it at about 25,000 miles an hour, never comes back. It keeps rising slower and slower because Earth's gravity is always pulling back on it, so it's always losing speed. But the farther it gets from the Earth, the weaker Earth's gravity gets, so the rate that it's losing speed keeps tapering off. And if you threw it fast enough, gravity just never catches up with its upward momentum, and it just never, escape velocity is the minimum necessary speed for it to reach infinity, which of course would take an infinite amount of time, so it never comes back. So anyhow, conservation of energy. The kinetic plus potential energy when you launched it, the initial energy, equals kinetic plus potential energy final. Final being at infinity. You can throw it even harder and it'll still have some kinetic energy left when it gets to infinity, but the minimum would be if it ends up with 0. Kinetic energy is 1/2 mv squared. Potential energy is the formula from the box. Incidentally, if anybody's wondering whatever happened to that nice simple little equation, potential energy equals mgh, that is for a uniform gravitational field. That would be the gravitational, I know it's the previous page now, but that would be the gravitational equivalent of the parallel plate capacitor that was on the top of the previous page. Between the floor and the ceiling of this room, there isn't any significant difference in the strength of gravity. For all practical purposes, you've got a uniform field, potential energy in a uniform field is mgh. But if you go throwing things into space, that's no longer true. And the amount of potential energy decreases as 1/r to the first power like we have here. So this is what you have to use when there's a significant difference in your distance from the center of the Earth as the thing moves. ME is the, just like in the inverse square law for force, M1 and M2 are the masses of the two objects that are attracting each other, which in this case is the Earth. ME is mass of the Earth. The M without any subscript, same mass that's over here in the kinetic energy, that's the mass of the projectile that you've thrown into space. Over here on the after side, well, for the minimum necessary energy to just barely get to infinity without turning around and falling back to Earth, kinetic energy final would be 0. The minimum initial velocity would be what leaves nothing left over for any kinetic energy when it gets to infinity. And the final potential energy is also 0. Because when r is equal to infinity, you know, you've got this really big denominator, which gives you a really small fraction. As r approaches infinity, the potential energy approaches 0. So something that will fall back to Earth has a negative, you know, the total energy, kinetic plus potential. Something that will fall back to Earth has a negative energy. Something that can escape is at least 0 or positive. It's the exact same situation you have when you get into atomic physics, only you're talking about the Coulomb's law force instead of gravity. An electron in a bound state in an atom has a negative energy because it's less than the atom's escape velocity. The kinetic energy of the electron is positive, but the potential energy is bigger and it's negative. In the bound states, electrons have negative energies. If you get the electron's atom up high enough to ionize the atom, so the electron escapes, then that would be a positive energy. So same thing with electricity that happens here with gravity. So you can, well, maybe I'll write it down before I cancel anything more out. 1/2 times the mass times V initial squared equals G times the mass of the projectile, mass of the Earth, over radius the projectile's original distance from the center of the Earth would be the radius of the Earth. If the thing was launched off the surface of the Earth. Divide through by the mass of the projectile and it disappears. The escape velocity doesn't matter if you're throwing a big cannonball or a little one, it's the same escape velocity. So you multiply both sides by 2 and then you take the square root and the necessary initial velocity for the thing to escape. Or I suppose if you really want to nitpick with your terminology, I should call it escape speed rather than escape velocity. Incidentally, just a little footnote. If you set the escape velocity equal to the speed of light and rearrange this to solve for the radius, that's the formula that gives you the gravitational radius of a black hole. Now, the very strong fields, Newton's model of gravity turns out to be a weak field approximation. You get into the really strong fields like around a black hole or a neutron star, and Newton's model breaks down, it doesn't work. You need to use the general theory of relativity in those kinds of extreme environments. So something that was derived with Newtonian physics has no right to work in that kind of situation, and yet just the same, it does. If you derive it correctly using the general theory of relativity, you get the same formula. You put the mass of the body, the mass of the star, or whatever it is that you want to calculate the gravitational radius for. You put that in there, you put the speed of light there, you solve for R. That's the radius of the Schwarzschild radius of the black hole. Anyhow, filling in the numbers for the Earth. Incidentally, you could calculate a gravitational radius for anything. You could calculate how big it would be if somebody made a black hole out of you, put maybe 100 kilograms or something in there for the mass, and turns out you have this little tiny black hole that would be like way smaller than an atom. We don't know how to compress a person down and make them that small. That's why there aren't any little black holes that size. But anyhow, I go off on a tangent there. Let's finish this off. 6.67 10 to the negative 11th power. Mass of the Earth, 5.99 times 10 to the 24. I would label that as being kilograms, except I've run out of blackboard. And 6.32 0.7 10 to the 6 meters. That's the radius of the Earth. All three of those numbers can be looked up in some table in your formula sheet. And so you run all that through your calculator. And it comes out 1.12 fourth. Meters per second, which might be more meaningful to some of you in miles per hour. That's very close to being 25,000 miles an hour. For other planets, escape velocity would be something different. If you're sitting on some little asteroid that's, you know, just a couple miles in radius, you could just jump off of the thing and you'd be going faster than escape velocity. So if you ever find yourself sitting on a little asteroid, you might want to keep that in mind. Sudden movements could be dangerous. Superposition principle. At the end of section 1, we looked at superposition of forces and fields. Now, superposition of energy or potential. And when you say what the word superposition means, it sounds like pretty much the same thing. Just take what you get from each individual source and add them together. The difference is in what you have to do for the word add. The fields and forces are vectors. So you have, you know, vector arithmetic, the components and all of that sort of thing. Energy and potential are scalars. So just as one of the more common mistakes in section 1 is people treating things that are vectors as if they are scalars, one of the more common mistakes in section 2 is people treating things that are scalars as if they are vectors. These things are just numbers. You just add them up. If you start multiplying by sines and cosines, you are just barking up the wrong tree. So, for example, same situation I had near the end of section 1. Same electric dipole. The question back there was to find the field vector at point P. Now my question is, what's the electric potential at point P? That goes like this. Superposition principle says the potential there due to both charges at once equals the potential you would have if only one of them was present, plus the potential, the voltage in other words, if only the other one was present. Both terms come from the equation in the box at the top of the page. V equals the Coulomb's law constant times Q over R. For the positive charge, you put in a plus Q. For the negative charge, put in a negative Q. And then you add. And since these two terms are the same absolute value with opposite signs, just adds up to 0. And that's all there is to it. When I was finding the electric field vector, I started over here, and I didn't finish the problem till I was over here, I think, because you had to find all the components and all of that sort of thing. Again, these are scalars. They're just numbers. You add them up, almost seems like, you know, too easy. Well, I suppose I can find a way to make it harder. So we'll move on to number 7. Same thing here I said about the gravitational problem that I did in section 1. Nobody would ever actually care about the potential energy of a group of, you know, 2 kilograms here and 4 kilograms there. Where this sort of thing comes up is in astrophysics, where you might have a small cluster of 4 stars. And what's the binding energy of that cluster? But then, you know, you're using big, ugly numbers, 10 to the 30th kilograms. And let's just illustrate the principle with nice little numbers that are easy to write, keeping in mind that that's actually what you're talking about. Also keeping in mind that the same principles are involved with electrical forces. This might be some molecule that has 4 atoms in it. And the potential energy stored in the bonds would be kind of the same sort of story. So first of all, part A, what is the potential energy of the 2 kilograms? One at the upper right. In other words, if I reached in there and grabbed that 2 kilograms and dragged it away from the others, how much work would I have to do to move it out to infinity? Okay, move it far enough away that there was no meaningful force from the other 3 masses. Let's see, where am I pointed? So part A, potential energy of the 2 kilograms. Well, it's a superposition thing. This is still under the heading of the superposition principle. As you go dragging that mass away from the others, how much work do you have to do against the field of the 1 kilogram? How much work do you have to do against the field of the 3 kilograms? How much work do you have to do against the field of the 4 kilograms? With all of them present at once, add those things together. So the potential energy that the 2 gets from the 1 kilogram plus the potential energy that the 2 kilogram gets from the 3 plus the potential energy that the 2 kilograms gets from the 4. Each of those 3 terms is given by the formula, well, it was at the top of the page, it slid off the top of the screen now, but it's negative g times m1, m2 over r. And I don't feel like writing the gravitation constant 3 times, so let's use the distributive property and factor it out, so I only have to write it once. So the energy that the 2 gets from the 1 kilogram, you put 2 and 1 in the formula for the masses. And the distance between them, the 2 and the 1, are 4 meters apart. Take that off the diagram. And so on. The 2 kilograms and 3 kilograms start out 3 meters apart. The 2 kilograms and the 4 kilograms start out 5 meters apart. I don't know if I'm going to get to part. Yeah, I might. Anyhow, 2 over 4 is 0.5. 2 times 3 over 3 is 2. 2 times 4 over 5 is 1.6. You add those three things together, multiply by the gravitation constant. I forgot to turn off the middle light, but I guess you can read that all right. Part B. Asks for the potential energy of the entire system rather than the potential energy of just the one mass. In other words, how much work would you have to do to completely disassemble it? Move all 4 masses so that they're infinitely far away from each other. Well, that's just an extension of the same process I started talking about in part A. After you've dragged the 2 kilograms off to infinity and done this much work, you grab another one. How much work do you have to do pulling that one to infinity? Once you've done that one, grab another one. How much work do you have to do pulling that one to infinity? You add it all up, and that's the potential energy of the entire system. Or to phrase it another way, it's the binding energy of the cluster. It's the amount of energy needed to take the cluster apart. So imagine taking the masses to infinity one at a time. Let's say that you take the 2 kilograms first, because I've already calculated that. The amount of work done. The amount of work done to take the 2 kilograms to infinity, where its energy would be 0. Well, that's the thing I just got done calculating. The gravitation constant times that term and that term and that term. Let's say after you've done that, maybe the next thing that you do is you take the 1 kilogram to infinity. The work done this time, well, if you grab this one and start dragging it away against the attractive force from the others, it's going to be attracted to the 4, and it's going to be attracted to the 3. So the work you have to do against the gravitational field of the 3 kilograms would be 1 potential energy of the 1 kilogram because of the 3 kilograms would be this, put the 1 and the 3 on top. The potential energy of the 1 kilogram because of the 4 kilograms is that. And that's all. You don't have a term for the 2 kilograms because you removed the 2 kilograms in the previous step. The 2 is gone. Next, you grab the 3 kilograms and drag it off to infinity. Well, the only thing that's left to attract it is the 4. Both of the others are gone. So the potential energy of the 3, because of the field of the 4, and they start out 4 meters apart. And then finally, when you go back to move the 4 kilograms, there's nothing attracting it. They're all gone, so you get to move that one for free. There is nothing left to pull on it. And then you add them up. Before I actually write down the answer, let's take what I've just done for this one specific example and kind of make it into a general rule that you'd follow no matter how many objects are involved. You add up the potential energies using that, U equals G M1 M2 over R. You do that for every way there is of taking the objects 2 at a time. Every way there is of pairing them up. You write out a term for that, and that gives it the potential energy of the entire group. When it's the potential energy of just one member of the group, you do every way of pairing them up that involves that particular mass. Potential energy of the entire group, every way of pairing them up that there is. So add the U's, the potential energies, for every way of pairing them, which is gravitation constant times 0.5 plus 2.0 plus 1.6 plus 3/5 is 0.6. 4/3 is 1 1/3. 3 times 4 over 4 is 3. That's every term there is. And I guess I can squeeze the answer in on the bottom. So potential energy of the entire group is negative 6.03 times 10 to the negative 10 joules. That's how much energy you'd have to provide to get this whole group up to an energy of 0.